The second question around stochastic gradient is how do you pick the step size eta? And this is a significant issue, just like it is with gradient. Both of them, it's kind of annoying, it's a pain to figure out how to pick that coefficient eta, but it turns out that because of the oscillation in stochastic gradient, picking eta can be even more annoying, much more annoying. So if we go back to our data set when we've been using it, I've showed you this blue curve many times. This was the best eta that I could find, the best step size. Now, if I were to pick smaller step sizes, so smaller etas, it will behave kind of like regular gradient. It will be slower to converge, and you'll see also less oscillations. But it'll eventually get there, but it'll be much slower. So we worry about that a bit. On the other hand, if instead of using the best step size, we try to use a larger step size because we thought we can make more progress more quickly, you'll see these crazy oscillations, and the oscillations are much worse than you observe with gradient, and I showed you with gradient. And so you have to be really careful. If you pick eta too large, things can behave extremely erratically. And in fact, if you pick the step size very, very large, you can end up with behaviors like this. So this black line here was an eta that was way too large. That's a technical term here that we like to use. And in this case, the solution is not even close to anything we got, even with bad etas with lots of oscillations, the ones I showed in the previous slide. It's a huge gap. And so eta too large leads to really bad behavior in stochastic gradient. The rule of thumb that we describe for gradient, for picking eta, is basically the same as the one for picking step size for stochastic gradient, the same as for gradient. But unfortunately, it requires much more trial and error. So it's even more annoying. And so you might spend a lot of time in the trial and error. Even though it's 100 times faster to converge, it's possible you spend 100 times more effort trying to find the right step size. Just be prepared. But we just try several values, exponentially spaced from each other, and try to find somewhere between an eta that's too small and an eta that is too big, and then find one that's just right. And I mentioned this in the gradient section, but for stochastic gradient it's even more important. For those who end up exploring this further, there's an advanced step where you make the step size decrease over iterations. And so, for example, you might have an eta that depends on what iteration you're in, and often you set it to something like some constant here, eta 0, divided by the iteration number t. Iteration number. And this approach tends to reduce noise and make things behave quite a bit better.